Hello everyone, and thank you for joining us today on the webinar titled Speed Up the Contact Analysis Process with MSC Nastran Solution 400. My name is Nicole Drake. I'm a Press and Marcom Specialist with MSC Software, and I will be the host for today's webinar. Our presenter for today's session will be Farnaz Jadbabi, Product Marketing Manager at MSC Software. Now I'm going to pass the presenter to Farnaz.
Thank you, Nicole. Hi, everyone. My name is Farnaz Jadbabi, and I'm the Product Marketing Manager at MSC Software, working with MSC Nastran and Mark. Thank you for attending this webinar. Today's presentation will be about some of the features in MSC Nastran Contact Solution 400. Okay, let's start. The agenda for today is to give you an overview of the contact analysis in MSC Nastran and kind of show you how you can define and create the contact bodies. Later we will have a short discussion on the different contact methodologies, whether segment to segment or node to segment should be used. And we will also discuss some of the new enhanced features that have been recently added to Nastran for version 2017 and 16. Before that, I would like to give you a short background of what's the benefit of having contact analysis. The analysis of contact is important because of the requirement to accurately track the motion of multiple geometric bodies and how these bodies interact with each other after or before when the contact occurs. And the objective is to detect the motion of the bodies, apply a constraint to avoid penetration, and also apply the proper boundary conditions to simulate the frictional behavior if it exists, or to simulate the real behavior of the structure. So what is contact analysis? Contact analysis is the analysis or the technology that allows you to speed up the process of assembling large parts and connections. So you can see here we have an example of an assembly, and it involves several steps. Several industry challenges can be observed where countless hours are spent for aligning the meshes and nodes of the parts that are not connected and don't have congruent meshes. And this will be important to structural analysis when they want to deal with large assemblies. And for the model assembly perspective, it's very important to have an integrated structure so the structure doesn't have any rigid body motions and the parts move thoroughly and properly. And so many of the parts come from various sources or divisions and departments, and this is a challenge to assemble these properly and quickly. So this is why the contact procedure can be very useful. And this way we can detect the motion of these bodies and parts and easily try to assemble them without having to deal with the node to node, like trying to connect the nodes manually and or remeshing the parts. As you can see, there are several steps, not only two steps for it. Generally, the contact often occurs before deformable bodies or rigid bodies, and sometimes one of these bodies is rigid because it's significantly stiffer than the other deformable body, and that's why we call it a rigid body. And so the first step for us to define the bodies and distinguish which parts are connecting to each other. As you can see here from this image, we have a body 1 and a body 2 for this slug and pin. And then later we define how these bodies are interacting with each other and what are they, which bodies are connecting to each other. Are they touching? Are they glued? So these are the topics that we're going to be discussing in this webinar. So just to give you an overview of sample applications, the simulation of many physical problems requires the ability to model the contact phenomena because everything in real world kind of faces this contact phenomena. From your everyday structures that you work with, everything has to have this concept of contact, and it's important to understand how it works and to deal with it properly. For example, when we are dealing with assembly modeling or interference fit or rubber seals or tires for crash analysis or in manufacturing process, along so many of the processes we use this phenomenon. And engineers from leading companies in many industries can use MSC Nastran for large-scale assemblies to deal with their simulations. Some examples that you can see here are shown, for example, for the auto industry, for the aerospace industry, even if you're dealing with microprocessors or electrical components, or even in the oil and gas industry, we see that the contact can be used to calculate and simulate these type of analysis. So the examples are not only found in the traditional aerospace and automotive industry, but you can see other industries as well. And so it's in the, for example, in an electronic industry, we see the printed circuit board assembly. So this one is also an example of a contact. Imagine that you had to make the nodes congruent on the circuit board. That would be very tedious and would require a lot of time. So that's why the contact capability can help you to quickly assemble the parts and calculate the stresses or any type of results you would like. So what are the benefits of contact over the previous methods? Some of the advantages we can see. First, let's say, what were the previous methods that were available to engineers? For example, the linear gap or the C gap. These methods are tedious and it requires more time. You have to manually find the nodes and select the nodes. So this is not very efficient. So contact is far more productive and efficient, and it requires less effort. As you can see, so you don't need to use the linear gap procedure anymore, and with the contact you can simply pick the bodies and just define how you want the bodies to interact. And contact is very versatile. Different types of contact is available. You can have solid-to-solid contact, solid-to-shell, beam-to-beam contact. So they have made it a way that it can cover a wide variety of analysis types, and you can also have solid-to-shell, shell edge-to-edge, and different types of contact. You can have thermal contact and calculate the heat transfer between parts, or you can have a coupled thermal mechanical type of contact analysis in solution 400. So it's a very versatile solution. Also, another benefit of using contact is the accuracy, which is very important. As you can see here, I have two pictures. On the left side, we have the two plates contacting when there is no contact defined, so structures are not aware of each other. So if you look at the deformation, they may pass through. But then when we have the contact, it's, the load path is changed. So for complex assemblies, how the load is transferred from one part to another is very crucial when it comes to calculating the accurate stress distribution. So, and contact gives us this advantage to understand the load path better. And contact can be used to accurately find out the load path and see how the load transfer happens between different components. Also, with MSC Nastran contact, the moment transfer between shells and beams to solids is also included. So that also gives more accuracy when it comes to analysis. Now, what's the benefit of using contact in solution 400? Why do we need to use Sol 400? Generally, contact is inherently nonlinear. The terms linear and contact are almost immediately in conflict. So it doesn't, although we may have it in solution 101, but the nature of the analysis is nonlinear. Because the contact problems need to track the deformation of the nodes and see if the nodes are coming into contact or not. And for almost most of these cases, the deformations are very large enough to invalidate our assumptions for a linear solution. So the assumptions on a linear solutions are that the deformations are small and the load path, the load and results are linearly related. But when it comes to contact analysis, usually the deformation is larger, and we can see also as far as the strains and the material properties, let's say. If strains are approaching 5% or higher, a rule of thumb is to say that the deflection of any node in the model is approaching 5% or higher, or the strains are approaching 5% or higher, and the deformation is 5% higher than the smallest dimension. In this case, you know that it's better to do a nonlinear analysis to be able to detect the real behavior of the structure. So that's why we prefer using the contact in solution 400. It also gives you the capability to use buckling, nonlinear buckling analysis if you want to do so. So you can run the model and load it when you have contacts in it in solution 400 and apply the incremental load to understand where the structure is going in stable, and that would be your buckling load. This is a benefit that's available. And also you can use the both preload with large deformations or rotations in solution 400. For example, here you can see the displacements of are large in this kind of analysis. And the first animation, you can see a track and a roller structure. You see how the displacements are very large and large deformations. So this kind of analysis is not going to be very accurate if used in solution 101. It's not going to capture the real behavior. And also for the both analysis, it's important to take the consideration of the preload, and we also want to know how the structure will behave, how strong the joint is, and the goal is to know and make sure that the joint does not separate when the actual load is applied under the loading. And also we want to make sure that we're not losing the preload. And the way that Nastran works is like we have each body considered as a separate contact body, and then the load can be split in half and the preload is applied. So for more details, you can always refer to the nonlinear user's guide. So some other advantages of using solution 400 for contact analysis is the capability to use thermal contact. Thermal contact allows to accurately capture the thermal gradient between different components. It can be glued or it can be touching. So you can see from the top model on the right hand side we have the glued contact, and then on the lower one we have the thermal touching one. For the glued one, you can see the temperatures are very continuous across the interface due to the contact. And as far as the touching one, you can use a touching contact to simulate the contact resistance between the bodies. You can see this here, that there is a temperature drop between the two parts when we're using touching contact. Another option that's available in solution 400 is the coupled thermal-mechanical structural analysis. So the multi-physics analysis allows the temperatures to be passed at each increment to the subsequent structural analysis. And this is much, much faster when done in solution 400 in comparison to solution 101. And you can even perform this type of analysis with structures that have different meshes using a restart procedure. And MSC Nastran allows the temperatures to be interpolated from a different mesh model, as I said. And this is a useful tool that's available in solution 400. Here, for example, in this, we can see the friction heating. This is also considered in the coupled thermal structural analysis. It's a capability that is available and can be used. And you can see here that when we run the analysis, the temperature of the block is rising as the model goes through. So these are some of the capabilities that are available in Nastran Solution 400 when it goes to contact. Now let's talk about different methods for doing the contact analysis. What is the technology or what is the methodology in MSC Nastran contact? So there are two methods to implement contact constraints. Historically, the first one is known as node to segment. In this case, a node makes contact with a rigid surface or an edge or a face of a deformable body or a rigid one. In the node to segment method, during the incremental procedure, each potential contact node is first checked to see whether it is near a contact segment or not. Then the motion of the node is checked and to see and make sure to see whether it has penetrated or not. So for this reason, we define a contact tolerance that's associated with each surface. So if a node is within this distance tolerance, then it is considered to be in contact. So here on the left side, you can see how a node is going to be projected to the surface. And in this concept, we use a slave and a master body, and the slave would be the node that is going to be touching the master. So the master is going to be the touched body. And then once this check is done and the contact node is detected, then the MPC is created between the segments. And it's important to note that although it's an MPC, but it doesn't rigidize the surface. So it's more of an RBE3 type rather. It doesn't add a lot of stiffness. It doesn't rigidize it. And there is another method available, and the second method is known as the segment-to-segment contact. In this case, multiple auxiliary contact detection points are placed on an edge or a face of a body, and contact technically occurs between these points or segments. So a constraint is formed between these points, and in this case, there is no master-slave arrangement for the bodies. So this makes it a little bit easier. And because this approach uses more target points between the bodies, there is a better stress continuity. So in general, this segment-to-segment method is more accurate, and in most cases is the recommended method. And for example, here you can see on the right-hand side, we have a segment-to-segment between a shell and a solid, and then we have the same model running using the node-to-segment, and we can see the segment-to-segment, the contact is detected better. This is a plot of the contact status, where you can check which areas are contacted once you run the analysis. So contact with shell elements with the segment-to-segment exactly treats the geometry of the element. So this is a benefit as well. Although other concepts such as separation and distance tolerance and these type of things can be treated differently, some of the concepts between the node-to-segment and segment-to-segment can be similar as well. And the same methodology goes as well as you have to define the body and then also define how these bodies are interacting with each other. And it's also important to note that segment-to-segment is available in solution 400 and solution 101. But in general, for analysis types where you're dealing with nonlinear properties such as large strains or large displacement, it's more recommended to use the solution 400. And how you can define this is on the method entry on the DC parabolic card. So if you want to know more and learn how to define these in Nastran, you can always refer to the MSC Nastran Quick Reference Guide. You can see also from this image that the entire shell edge face is glued. So we're using a glue one in this example in comparison to the one on the left side where you see that only some portions are included. So the whole thickness and the entire face of the shell is included in contact when using segment to segment. So this creates more accurate results. So some of the tips actually as far as using contact analysis and which method is better or which, although both methods are accurate, but generally, as I mentioned, we recommend segment to segment. Now, if you're using node to segment, sometimes it's hard to define what body to pick as slave and which one is the master. The rule of thumb is to have the body with the finer mesh as the slave and the one with the coarser mesh as the master. For many problems this works, but if the problem is a little bit more complicated, we may not know exactly which body has a finer mesh. In this case, there are some tips that may be useful. Again, these are some general options, so every model is different, but in general, we recommend that in the case that you don't know, let the program decide which search order to pick from slave to master. So let the program decide. In this case, you want to use the iSearch entry to equal to 2, so then the program can do the single order search. Now, this is to avoid the penetration that may happen due to the different mesh densities. So in this case, it's recommended to use iSearch equal to for single order search. And what is iSearch? iSearch is simply an entry in Nastran. It's the flag that dictates what search method to use from slave to master, from master to slave. So there are several options available, and you can refer to the quick reference guide for more information on those. Another useful tip is to use the optimized contact inside Nastran. In this case, the solver decides to do the double-sided contact with the optimization of contact constraint equations. This is another option that's available. For this one, you just set the IS type equal to 2. So these may work for some examples if you don't know which body has finer or which body has coarser mesh. But in general, if you decide to switch to segment, you don't have to deal with the master and slave methodology anymore. So while both methods are very accurate and can give you good solutions, the node to segment technique relies on a discrete numerical method, while the segment to segment uses the continuous approach. So in this case, you will get a better stress continuity with segment to segment. So you can see here from this image, the one on the right-hand side, we have here we see a smoother stress plot. And so we have this better stress continuity in comparison to the node to segment. This is an interference bit example between two disks with different mesh discretizations. So also, the concept of slave to master may be a little bit difficult when it comes to shells with multiple layers and multiple contact bodies due to the thickness. Although you have the option to include the shell thickness or ignore the shell thickness, but in these kind of cases, I think segment to segment contact is a little bit easier to deal with. So that's why this concept was developed in MSC Nastran. Now that we have covered some of the theoretical concepts, let's see how we can approach the process. So there are contact bodies, two types of contact bodies, the deformable contact bodies or the rigid ones. In this here, we're defining talking about the deformable contact bodies. And you can see that these type of bodies can have a stress and temperature distribution, and generally there are a collection of finite elements. So you can see here it has the mesh, and the deformable surface is simply and easily defined by the set of elements that comprise the whole body. And you don't have to literally go and pick the elements, like you don't have to define which part are going to contact. Nastran will take care of that. You just pick the section, and Nastran is smart enough to know which nodes or which parts are coming into contact. And there are several methods available to create the contact bodies, to create the deformable contact bodies. One of them is to define them by groups. In Nastran, those will be by Nastran sets. The other method is to define them using their properties. Let's say if you have some elements defined on a plate property or a P-shell, then you can use those and assign the unique property ID and make that a deformable body. And also you have an option to use the graphic user interface. For example, here I'm showing Patran. We have a very cool tool in Patran. Inside the Solution 400 preference of Patran, you see this tool that automatically creates several contact bodies for you. So it's under Tools, Modeling, Contact Bodies Creation, and this gives you several options based on connectivity, based on the element type, based on properties. So it's a really quick method to create several contact bodies at once without going to the make them one by one. So that's a cool feature to use. Now, there's also another type of contact bodies available in Nastran, and those are called the rigid contact bodies. Again, as I said, sometimes the contact body is much stiffer, so that's why we call it rigid. And these surfaces do not deform. So for most rigid bodies, the geometry is generally defined by an analytical 2D nerve curve or 3D nerve surfaces. Nerves are mathematical representations of a geometry. These analytical methods are very advantageous because they lead to a better accuracy in the representation of the geometry, especially when it comes to curved surfaces. So it gives you a better and more accurate calculation result, also a better representation of the surface normal. So here you can see we have a contact, a rigid surface that is moving and pushing on our deformable body. And so with the rigid surface, rigid bodies, they can be 2D curves, or they can be curves, 2D curves or 3D surfaces. So you can have in Patran, you can have the geometry, or you can bring in a CAD geometry, or you can create the geometry and define it as a rigid body. And here I'm showing you how you can create it in Patran. There are several ways. One is to go under the rigid body form and do the create, or you can see here from the contact bodies group, you can just simply click on rigid. And generally within the analysis, these rigid surfaces are treated, as I mentioned, in two methods. So there's the discrete or the analytical one. And I think Patran does the analytical one. And the discrete one consists of patches or straight segments, whereas the analytical one is more continuous and more smooth. So the method to define the motion of the rigid surface, you have three options in Nastran, and you can see here in this form of Patran, I'm showing how you can view this or access it. There is you can define the motion of the rigid body by prescribing the velocity for it, or prescribing the final position, or displacement, or the other option is to apply a load or an enforced displacement. And generally, the decision on which method to use is up to the user. It's dependent of, it's dependent to the model, and technically there is no rule on which one to use. But for most cases, when the load control method is used, if you want to specify a translational load or a rotational load, two additional nodes are applied and assigned to the body. And these nodes are called the control nodes. So one is to define the rotation that was applied, and one is to define the translation. So as I mentioned, there is no need to mesh these rigid bodies. So this makes it much simpler as well. You can simply import the geometry, or you can create it. Once we have defined our deformable bodies, it is time to specify how these bodies are interacting with each other. So this is an important step, right? The first step was to define what parts, what assemblies we want to use in the contact. Now we have to say which ones are contacting each other, and if they are, what type of contact is it? Are they glued? Are they touching? So This is the third step that can be done using contact pairs or contact tables. Generally, I prefer contact pairs. The newer method of contact pairs gives you more control, and it's very, very suitable when you have multiple bodies. Let's say in cases where you have hundreds or thousands or more than a few bodies. So it's much more convenient. Again, in Patran, you can use the same form to automatically create these body pairs from tools modeling. As you can see, it's an automatic method. Here, the tolerance distance that's given is the distance. This is different than the actual distance tolerance on the node, so don't get it confused. This one is the distance that Patran will know which two bodies to assign a contact pair to. And also, you can, if you don't want to use the automatic approach, you can go to the actual loads and boundary conditions form and then select to create the body pairs for multiple contact bodies. So for every two contact bodies, you will make a contact pair. And once you've made those, you can always click on that button and use the color code method to color code your contact bodies. This is a very useful feature that allows you to see them inside Patran. So when you make the contact pair to define how these two bodies are interacting, you have to define whether they're touching or whether they're glued and some other parameters. So the default is touching, but if you want to switch it to glued, you can see on the very right-hand side form, there is an option to change it to the glue. Once we have defined the contact pairs, it's important to define additional contact parameters because every contact problem involves a variety of different geometric or kinematic situations. So every problem is different, but there are some general approaches that can be used. So one of the items that you have to define if you're using the node to segment method, as mentioned before, is the distance tolerance, or the distance between which the two nodes are considered in contact. This one is one of the geometrical properties of contact, so that's why we call it under the beacon PRG entry inside MSC Nastran. And in Patran, when you're using contact pairs, you can go to the properties form, and for each of these two, the beacon PRG and the beacon PRP, you'll see an option in Patran under the properties form, which makes it much easier to define these parameters for multiple contact pairs. Instead of going for every single one and defining, let's say, the distance tolerance, you can just globally change the tolerance for all your contact pairs using this form in Patran. So you just go to the Create 3D Body Pair under the Properties tab, and you switch it to geometric or physical. So some of the geometric entries, for example, are the tolerance, the bias factor, the initial gap or overlap. And some of the physical physical entries could be the friction, the separation, or if you want to define, let's say, the heat transfer coefficient. So these are some of the entries that are available. Now, when defining the contact tolerance for the node to segment, although the default value may be used and successfully running for most of the problems, sometimes, if you want, you may need to switch it. So if one has inside knowledge, then it's much better to utilize this option for the contact pair. Now, the size of the contact tolerance will have a great impact on the computational cost because if the accuracy of the model and the computational cost can be dependent on this error tolerance as well. As you can see, like here on the right hand side, we have the distance. So you can see the green node is the slave contact body node that is going to be projected to the master contact body surface, and the distance tolerance is shown here. On the left hand side, I'm showing you the option with the bias. Bias kind of helps to improve accuracy of the results. And also, it's important to mention that the bias factor for glued is 0, so it's not used for glued, but for touching contact, you have a default value of 0.9, I think. For more information on these, you can refer to the quick reference guide. So it's important to define the contact tolerance properly, because if the tolerance is too small, the detection of the contact is hard, and then penetration is going to be happening, and the load transfer will be not properly defined. So if the contact tolerance is too large, nodes are considered in contact prematurely, and then if the contact is too small, then the contact is not detected properly. Now, the different types of contact you can see here are glued and touching contact. We have several types. One type is the permanent glue, and permanent glue is a special case of contact based off the initial condition of the bodies with respect to each other. So the contact changes in permanent glue are not considered throughout the analysis. This option is just a quick and easy way to connect the dissimilar meshes for the cases where the deflections of the overall structure are negligible and the stress distribution near the contact area is not important. So this one is going to create a linear MPC equations between the nodes. So it's just a quick method of connecting the nodes. But the method that's more going to be able to capture the true behavior of the structure is the general glue. And in other words, we call it the nonlinear glue. And this option is available in solution 400 and 101. But again, with solution 400, you will get more options and more capabilities. In this case, the bodies don't have to be initially in contact. They can come in contact during the analysis and then become glued. And also, they can separate at any point in the simulation. But when they're in contact, we don't see any relative sliding. So you can imagine two surfaces that have an infinite friction. So it's important also to note, although we call it glue, the bodies may lose contact at any time if the separation force or stress that was defined is exceeded. So in this case, it can be separated due to unglue. Or users can define breaking glue, which is a different topic and which is not discussed here. Now, this is glue, and we've discussed the glue, but what about touching contact? For touching contact, parts can come into contact in compression and pull apart in tension. Compression loads are transferred, and the bodies may slide along each other's surfaces, whether the friction is there or it's not. So for touching contact, in order to calculate the real behavior of structure, it's important to include the friction if the model dictates so. And optionally, the load can be transferred when friction is defined. The tangential load can be transferred. And this is only available, the touching option is only available in solution 400 and 101 and 700. So in general, for other solutions, let's say similar to normal modes or buckling, linear buckling analysis or frequency response solutions, only the permanent glue is available, not the general glue, not the touching contact. Now, although the touching and the general glue are available in solution 101, it's important to note that the only source of nonlinearity in that solution is a contact. So no large displacement or rotations or material nonlinearity are available. Now, for the touching contact, another important option is that just like permanent glue, it's the incremental procedure because we're running it in a solution 400. So the status is checked in every increment. And the contact force will be checked against the separation force for contact separation once the solution converges. So bodies remain in contact if the pulling force is less than the separation force that's been defined. Otherwise, the contact allows separation. Here you can see an example of a rigid surface, rigid body touching a deformable one. This is a rubber seal, and you can also see that the body has self-contact. So this is another feature that's available. Not two bodies can contact each other, but a body can also contact itself during the when it's under the excessive load. Now, let's talk about the new features and enhancements that have been added to recent versions of Nastran. So the Nastran contact capability in Solution 400 has been widely used for structural analysis in the last years, and the feedback from the users was always good for us, and the feedback to see what's good, what's bad, what's painful, and it has helped us to improve and mature the contact capability. So based on the feedback we got, some of the new features have been available in the new releases, which I'm going to be talking about a few of them here. One of the good ones is the initial gap and overlap option, the option to maintain these gaps or make design changes if required. So now MSC Nastran has the capability to maintain the variation of the gaps and overlaps which exist between the parts. What are the reasons that the parts can have these gaps? One of the reasons is the modeling approximations, or sometimes it's the geometry issues. And so the benefit is that the Nastran allows you to do that without even moving the nodes. So you just define the initial gap capability. And it's important as for you to note, it's called initial gap, so it's going to happen in the initial step. So it allows the user to set the gap clearance to 0 if they want to. It also allows them to maintain it depending on the application, and it's also specified in the initial step. And you can define it on the Beacon PRG as mentioned in my previous slide. This is a parameter to define the geometrical options. And what are the applications? For example, in many cases, we see that there is a gap between parts because there's been shims during the production, and so it's important to take that into account. You can see here, for example, in these plates, we have a gap, then we have some overlap, and then we have a gap, so it's very varying. Another option is for ply drop-off. Since we don't create the properties for each ply drop-off, the plate thicknesses are idealized and they have variable thicknesses, so these changes can create gaps and overlaps between the plates. So that's another useful place that the initial gap overlap capability can be used. Here I'm showing an example. You can see the user has the option to maintain the gap or to change it. So here for these two, you see there's a gap. Like at first on the left side we don't see a gap, and then the gap starts due to the shimming. Now the blue part is the shim, but this shim is not included in the finite element, so we're just putting it for better visualization. You see how the gap is 0.05, and but then the shim is installed at 0.03, so there is a remaining gap of 0.02. And users can simulate this with the option to keep the distance and also to shrink the distance. So you can keep the distance of 0.03 and then shrink the distance using the OPI-NGP entry or the MGI-NGB entry. So to know how to use these entries, for more information, you can always refer to the MSC Nastran Quick Reference Guide. Here you can see this helps with the initial contact status. So after we added this entry, the initial contact status is much, much better. You see the red nodes and you see the blue nodes, therefore slaves and masters, and you can see how this is much, much better and more accurate, so it gives you better results. The other option that has been added to Nastran is the segment-to-segment contact for beams. Beam contact behavior is encountered for many engineering applications, for example, in the oil industry or the drilling operations or in the automotive applications. So it's important to take proper consideration of beam contact and make sure we get the proper and accurate results. Beams are usually commonly used to support structures of shells in many aerospace and civil engineering applications as well. This includes the stringers and the spars and other items. Before this new feature was available in MSC Nastran, beams were used as an equivalent contact radius was used to take into account when it comes for contact. So that's why it was considering all the beams to have a circular cross-section. But with the new option to have in MSC Nastran, I think this was in 2016, all beam cross-sections are to be considered properly. You can see here on the image on the right hand side, the lower image for the segment to segment beam and shell edge, we see the proper cross section is defined. So this can be for any type of cross section, for circular tubes, for solid sections, for thin wall sections, I-beams, different types. And this is very useful, and it can be used with P-bar L and P-beam L options. And generally, the way that Nastran approaches is that all faces of the beam are treated as a patch, and the user have a control over how to define these patches or how many patches. This is also provided to the user. For example, here on the right-hand side, you can see an I-beam. We have about 12 segments. You can see the segments on the flanges and the web. So the total will be about 12. Also, you can see here in this image that when we did a node to segment beam and shell edge contact, the contact was not properly defined, and then with the segment to segment beam shell with the new feature, the contact cross section is defined properly and the contact is detected better. So here you can see the actual results. You can see the contact status, how you see more nodes are in contact due to the new feature that has been added. Last option that I'm going to be talking about is the cohesive contact capability that has been added to Nastran 2017. So cohesive, they call it cohesive contact or the flexible contact. In the modern industries, the product structures like airplane, automobile, and so on are becoming very and more complicated with many parts and assemblies. So the process may be done through a variety of parts, as you know, for example, the contact or C-gap or stuff. But the contact is the easiest way to assemble these parts, right? And so that's why we use the glue contact. But the glue contact provides the capability to effectively and efficiently simplify and reduce the computation cost and assemble the model. However, it may sometimes result in too stiff of a structure because effectively the connection is more stiff. Although it's not like an RBE2, although the MPCs created are not an RBE2 type, but it's a little bit more stiff in comparison to other methods. So in order to take into account for this and to get better and more accurate results, a flexible glue contact capability is available in Nastran 2017, or it's called the flexible contact or the cohesive contact. With this option, now it is unnecessary to model the detailed connectors, but the user don't need to do the, let's say, the C-gaps or the C-welds and these type of analyses to connect the parts, but then they can use the benefits of glue contact, however, without the stiffness effect, stiffening effect. Now, it supports mixed contact types like permanent glue with cohesive contact. It also supported for general glue with cohesive contact. It can have mixed contact type. It can be defined on the Beacon PRG, again, for the geometrical parameters of contact. And it also is a way to give you more realistic results for the fascinated joints. And the user has to specify the stiffnesses for the glued contact joints. And another item to mention is that is supported for segment to segment. Now, let's go back and look at the results. Once we run the contact analysis, the last step is to look at our results. Users have several options in the new versions of Patran and Nastran for 2017. They can use the HDF5 results, or they can still use the master DB-all or the new and enhanced OP2. These are some of the output files that are available to post-process contact results in Nastran for Solution 400 as well. The entry that's needed to obtain the contact results is the B output. This should give you contact normal forces, contact status, and several options. Here we can see a plot for contact results for every deformable body, and using the HDF5 for the Solution 400 contact results in Patran and Nastran 2017, you may be able to get the results faster and quicker for attaching the result file to Patran or for post-processing. So this concludes the presentation.
So due to today's time constraints, so I want to thank you all for joining us today, and have a great day.